In this video, I will use Matlab Simulink tool to simulate the performance of a mass spring damper system. Here's my model, a mass connected to a fixed support by a spring and a damper, and we have an external force F of t, general external force applied to the mass. The equation of motion of the system is standard mx double dot plus cx dot plus kx equals F of t. I will start by rearranging this equation of motion so that the acceleration term x double dot is on one side of the equation, the rest of the terms are on the other side. The first step I will do just in the previous, just like in the previous video, I will start by planting my state variables on my drawing board here by inserting two integrators. From the continuous menu, we'll have an integrator and another integrator here. Connect the two integrators together. Now the input to the first integrator and the output of the second integrator. The input here is the acceleration, and then we integrate the acceleration to get the velocity, we'll call it dx, and finally we integrate the velocity to get x. So now I have three lines on my model here that represent the state variables of the system here, x double dot, x dot, and x. Now x double dot, I'll go back to the equation here. X double dot is basically the sum of three quantities. So I will have to add a sum block here to add up all these three quantities to form the x double dot term. I will go to the commonly used blocks, and here's at the bottom the sum block. Okay, connect this here. Now notice that the sum block has two ports, two positive ports, but I have three quantities here, so I can go in and change the count, the port count in here. Now the number of symbols here represent the number of ports in the sum block. Now I have three symbols here: vertical column or vertical bar and two plus signs. The vertical bar represents a null port, or it doesn't show up on the block. So if I want to have one positive port and two negative ports, I will have to add plus, minus, minus. Now I have three ports, one positive and two negative ports. And here are the three ports. Now notice that Simulink distributes the ports in the left 180 degrees of the circle equally. Now if I want the three ports to show up in the left bottom quarter of the circle, then I will have to have 5 ports. But I don't need the two upper ports, so I will add two vertical bars before. Now I have 5 ports here, but the two upper ports, the first and second, will not show up. And here's my final sum block. On the positive port, I will add a force. Let me use step function just now as a placeholder. Here's my input. Now I have a negative term in x dot, so I will connect the first negative port to x dot and the second negative port to x. Now the x dot term is multiplied by c, so I will add again from the commonly used right here and inserted in line of the x dot feedback line, and then I will add another gain for k in the line of x. Now also if I don't want to go to the library browser every time, I can copy paste blocks, just regular Control C, Control V shortcuts, and here's my K, call it K, and this is C. Now let me add a scope to view the output. Okay, now we're almost done. We had the C, the K. We still have to multiply the whole sum here by 1 over m. That's the total sum, is the output of this sum block. So I'm gonna add again right after the sum block. Move this to the right a little bit and copy again block here. Okay, and this block is going to be called 1 over m, and here we have our complete model of a mass spring damper system. To make sure that everything is okay, I'll open the scope and hit play, and we have a response and no error messages. Now I will go always to the modeling page and reduce the maximum step size of the simulation. It's set to auto by default. You can use 001 or 005, depends on the speed of the system. So back here, and here's my response. Now let me use these parameters right here. I will use a 2 kilograms mass, so this gain will be 1 over 2. The damping factor, damping coefficient, is going to be 2 Newton second per meter, and the spring stiffness is 8. Hit play again, and we have a different response. Now we have two types of responses for a system. We have a natural response and a forced response. Now the natural response is basically when the applied force is 0, or when we don't have any external applied force. So instead of the step function, I'll go to sources and use a constant block. Let me delete this and set this constant to 0. Now the input to the system, f of t, is 0, so I will have only a natural response. So back to the scope and hit play, and nothing happens. Nothing happens because for us to have a natural response, we should have initial conditions. And where do we add those initial conditions? Obviously the initial conditions belong to the integrators part. So if I have, here's the integrator block that produces x, so the initial condition, double click here, on x will be in this block, and here's my initial condition. It's set to 0. So let me set this initial condition to, let's say, 1. And back to the scope and hit play. And here we have our natural response starting from 1 and going down all the way to 0. And that's what I expect from a natural response with no external force, a damped sinusoidal response, depending, of course, on the damping coefficient C, whether the system is over damped or under damped. Obviously, the system is under damped because we have sinusoidal response within the system. Now, I can also add an initial velocity to the system. Here's the initial condition in the integrator that produces x dot. I will set that to, let's say, 2 and hit play again. And here's the response. Starts at 1, that's x0, and it has an initial slope upwards, indicating that we have an initial velocity. The slope of the x is x dot, so the slope, initial slope, is positive. We have positive initial velocity. Now, in case I want to simulate the response using an external force, sinusoidal external force, 2 sine 2t. I will have to insert a source that produces a sine wave, and here we have a block in the sources called sine wave. Take that, insert it here, delete, put this aside for now, and then connect to the input port in the sum block. And on the inside, let's set the parameters. The amplitude of the force is 2, and the frequency is the term with the t, 2 radians per second. Okay, now let's hit play. Okay, and here's the total response. This includes the homogeneous and the forced response, the natural and the forced response together. The natural response is right here, and then with time the natural response disappears and only the forced response remains. I can increase the simulation time to 30 seconds to see clearly how the natural response in the beginning takes effect, and then because it's multiplied by a negative exponential function, a function with negative exponent, it dies to 0, and I end up with only a sine wave, or a sinusoidal wave, sinusoidal response representing the forced response. Let me add the force input to the scope here to see both signals at the same time. Okay, here we have it. Play, and the force is the yellow line and the blue line is the response. Notice that the forced response has the same frequency as the forcing function, but obviously there's a phase shift. You can, if we zoom in, let me use a horizontal axis zoom. We see that the wave, the force wave, hits the 0 on the time axis, hits the 0 at 17.25 approximately. while the response hits the 0 later on at 18.1. That's approximately a time shift of 0.85 seconds. And that time shift is basically the phase shift we see in the equation of the response when we solve for the analytical solution of the system. There's a phase angle phi, and that angle is basically showing up here as a time delay. And we know that to convert time to a phase angle, we have to just divide the multiply the time by the frequency, omega. The frequency of the response here is 2 radians per second multiplied by the 0.85 seconds time delay. That will give me the 1.7 radians phase shift in the response. So this shows the total response of a second order system, represented here by a mass spring damper system. Now, finally, few touches here that I can add. First, in the integrators, right here, notice that I can, here, the initial condition, it says the source of the initial condition is internal. That's where I input the initial conditions in this block. I can set this to external. Okay, and a new port appears here requesting x dot, requesting an initial condition. So for that, I will here connect this port to a constant and set the initial condition here, this constant, to 1. That means 1 will be the initial condition to this integrator block. Also for the first integrator, the initial condition will be velocity. I will set that to external. And here's the new port appearing. Now, this first one was x0 or x dot. Now I'll copy another constant and call it VO for initial velocity, and connect it to the integrator port. The initial velocity we chose was 2. Go back here and hit play, and there's the same response. Finally, to make things a little bit nicer and cleaner, I will select the whole model, the part that relates to the equation of motion, select it all, and then set it in a subsystem. Here's the options menu, and the first option is create subsystem. So everything now is placed inside a block called subsystem. I will call it a mass spring damper. And we have 3 ports. Port number 1 for the force. Double click, you see the content of this block. The output, out1, I'll name it X. The first input 1 represents actually the input force, F of t. The second port is connected to the first integrator, so that means it represents V0. And the third port connected to the second integrator represents basically X dot. So going back up now, 1 level up, and here we have our model, and the ports and port names are showing on this block. So that's basically how you simulate a mass spring damper system. Now, since the external initial conditions are here, external to the system. I can play with these initial conditions as I want and see what effect of the initial condition appears on the system right here. I can also play with the input, the sine wave. Let's maybe change the frequency to 1 and see what happens in the response. Again, all the time it starts with the natural response and then natural response disappears and we end up with only the forced response. You can increase the simulation time, let's say 2 minutes, and see all the irregular response in the beginning, the natural response disappeared, and we have regular sine wave response in the later seconds representing the forced response.